Each meter stick in the room has a different mass due to the knots of wood, the type of wood, the divots in the polyurethane, the amount of ink that's on the meter stick from magic markers. So you have to balance your individual meter stick using the knife edge. The knife edge goes down with the screw pointed downward toward the lab table. I'm going to read this along the edge, right along here. So this one appears to be 49.8. 49.8. Please record that in your chart on your lab. Okay, we're going to put 500 grams in brass on the left-hand side of our meter stick. It also says we need the measured mass of the slotted weight hanger. That is this. We're going to pop this on the triple beam balance. I got lucky this time around. It says it's 50 grams. It actually was when I put it on my zeroed balance. The next thing I have to do is I need the mass of my meter stick hanger. I'm going to get that on the triple beam balance and record it in my data table. The total mass will be the 50 here, whatever this one comes out on my triple beam balance, plus the 500 grams in brass. Add that all up and record it in your data table here. This is the first page of the lab, the torque experiment. This is the counterclockwise torque with 500 grams in brass on the left-hand side of the meter stick. We've got 50 gram mass hanger or weight hanger. We also have the measured mass of the meter stick hanger. That would be this little gizmo. Notice the screw is pointed upward when we're hanging our masses from it. My torque formula has been recorded at the top of the lab. I'm going to use the torque formula using the perpendicular force and distance. My lever arm is found here. My lever arm is the difference in the distance from where the mass is hanging to the fulcrum or the balancing point. Please keep that in mind for the entire lab. Do not change the left-hand side of this lab from now on. Leave it exactly as you see it with 500 grams. Do not alter it at all. The second page of the lab begins by my determining the mass of my meter stick hanger. They are not all the same. You're going to have to put it on the triple beam balance. Don't assume that the number you got on the first page is going to be the same throughout the lab. So once you've gotten the mass of this, you're also going to have to put the slotted weight hanger on your triple beam balance and find out what it is as well. We're going to regulate the lab. For the clockwise torque, I'm going to ask in trial 1 that you use 400 grams in brass mass. On trial 2, please use 200. And on trial 3, please use 100. In that way, we're going to regulate the key. So for trial 1, you need 400 grams on the right. You're going to have to move this mass until you get it to balance. the clockwise torque must equal the counterclockwise torque. We're getting pretty close. A little bit too heavy on the right-hand side. Once you find that balancing point, we're very, very close at that point. It's a little bit too heavy on the left. We may be able to alter that. These meter sticks have been used for this lab every year and they've been damaged. Looking pretty good. Once you have that balancing point, you're going to read it off here. So this is F1, D1. The lever arm distance is between where it is hanging and the fulcrum. This is F2. This would be D2, the difference in the distance from where the mass is hanging to the fulcrum or balancing point. After you've completed trial 1 with 400 grams on the right, trial 2 with 200 grams on the right, and trial 3 with 100 grams on the right, please find the percent error by using the theoretical minus the experimental divided by the theoretical torque. If you'll remember, your theoretical torque came from page 1 at the very bottom. Your experimental torque came from each of the data tables as you computed force times distance.